In this continuing review lecture, we'll talk about combining the forms that we've discussed in the previous two reviews to construct the Bode plots of more complicated transfer functions. So the basic idea here is that we can combine terms such as poles and zeros that we know how to draw the asymptotes for according to some simple rules. And the simple rules can be seen or derived really by writing the expression for a complex number in polar form. So suppose we have a transfer function g1 and another one g2 and g3, and we express each of these in the polar form as some magnitude that's called r here times e to the j times theta, the phase. So if we call g3 is the product of g1 and g2, we can find the magnitude and phase of g3 by multiplying the terms for g1 and g2 together. So we'll get r1 times r2 times e to the j theta 1 times e to the j theta 2. And the product then we can write as r1 r2 in magnitude, which is the magnitude of g3, times e to the j theta 1 plus theta 2, so the phase adds. Okay, when r1 and r2 are expressed in decibels, then their product is found by adding the dB values. So r3 is the sum of the dB magnitudes r1 and r2, and theta 3, the phase, is the sum of the phases. So in general then, to find the composite phase, when we multiply terms, we simply add the individual phases. And to find the composite magnitude in decibels, we add the composite dB individual magnitudes. So here's an example. Suppose we have a more complex transfer function that has a constant term, g0, that we'll take to be a real positive number, and then it has two poles. So there are two denominator terms that look like the poles that we previously discussed. And here are some numbers plugged in. So g0 is 40. If you express that in decibels, 20 times the base 10 log of 40 turns out to be 32 dB. F1, the corner frequency omega 1 over 2 pi, let's suppose is 100 hertz. Let's suppose F2 associated with omega 2 is 2 kilohertz. So here's a plot of that. And to construct the magnitude, we construct the magnitudes of the individual terms and then add their dB together. So G0 is 40 dB. I'm sorry, it's 40 or 32 dB, which is up here. So that's the G0. The first pole is 0 dB for frequencies below F1. F1 is 100 hertz right there, so here's F1. So we'll be 0 dB until we get to F1, and after F1 we have an asymptote that has a slope of minus 20 dB per decade. That was supposed to be a straight line. Okay. Then our second pole at frequency F2 of 2 kilohertz, let's see, there's F2. This one has 0 dB asymptote until we get up to F2, and then it has a minus 20 dB per decade slope after that. So to get the composite, we have to add the blue, the red, and the green lines, and at any one frequency, the composite magnitude will be the sum of the individual magnitudes. So, for example, down here at low frequency, we have 32 dB plus 0 dB plus 0 dB is a total of 32 dB. And we continue like that until we get to the first corner frequency at 100 hertz. After 100 hertz, the first pole adds a minus 20 dB per decade slope. So the composite will decrease with that slope because the first pole is decreasing, and so we'll follow this minus 20 dB per decade slope, until we get to the second corner at f2. At that point, we have another minus 20 dB per decade slope, and the composite will go down with a minus 40 dB per decade slope. So the yellow asymptotes are the total asymptotes for G of S. Likewise, to construct the phase asymptotes, we construct the individual phases of the different terms and then we add them together. So the G naught term is a real positive number, its phase is 0. The first pole at F1 gives us 0 degrees phase until we get to 1/10 of the corner frequency F1. So F1 is 100 Hertz, 1/10 of that is 10 Hertz, so here's F1 over 10, or 10 Hertz. Beyond that corner, this first term has an asymptote with a slope of minus 45 degrees per decade, and we continue at that asymptote, or that slope, until we get to the next break frequency, which is at 10 times our corner. 10 F1 is 1,000, so we're at 1,000 Hertz, and at that point we flatten out and have a constant minus 90 degree asymptote. Finally, our last pole has a similar shape, except its corner is at 2 kilohertz. So let's see, here's 2 kilohertz up here. 1/10 of that is 200 Hertz. So we'll follow a 0 degree asymptote until we get to 200 Hertz. Then we'll go down at minus 45 degrees per decade until we get to 10 times 2 kilohertz, or 20 kilohertz. After that, we have a minus 90 slope, or minus 90 degree flat asymptote after that. So the composite phase asymptotes for this transfer function are found by just adding the individual phase asymptotes. So at low frequency we have 0 degrees. When we get past 10 Hertz, the first pole makes our phase start to decrease. When we get to the second pole, or when we get to 200 kilohertz, 1/10 of the second pole, we get another break, and the second pole starts contributing negative phase as well. So the composite will have 2 phase asymptotes that are decreasing, and our total will go down with twice the slope, or minus 90 degrees per decade. So that's supposed to be a straight line there. When we get to 10 F1, or 1 kilohertz, the first asymptote flattens out, but the second keeps going, so we continue with a slope of minus 45 degrees per decade until we get to 10 times the second corner at 20 kilohertz, and after that all of our individual asymptotes are flat, and so the composite has a flat asymptote also of minus 90 plus minus 90, which is minus 180 degrees. So there, the yellow is the composite phase asymptotes for this transfer function. Let's do a second example. Here is a set of asymptotes that we're given, and the object here is to write the transfer function. So this is a transfer function A of S, and we're supposed to write what is the expression for A of S. Well, there's more than one way to do this, but one way is to say, okay, we're given what this low frequency asymptote is. It's A0. Here the asymptote is actually expressed in dB. We have to, when we write the transfer function, we have to write A0 that's not in dB, but just as a regular number. At frequency F1, the asymptotes change, and we have a plus 20 dB per decade slope. What kind of term does that? Well, a 0 would do that. So we could have a 0 function term in the numerator with a corner frequency F1, or in our transfer function we express this in the corner in radians per second, so omega 1, where omega 1 is 2 pi F1. We continue until we get to F2, and after F2 the the slope decreases by 20 dB per decade, and it goes back to a flat slope. Well, the kind of term that decreases the slope by 20 dB per decade is a pole. And so the transfer function A of S can be written in this way. Okay, we can also write expressions for the asymptotes, and I'm going to illustrate how to do that here. In order to write the equation of an asymptote, what we do is wherever we have a sum, we take the term that is largest, and this is in fact how we derive the asymptotes in previous lectures. So for example, what is the equation of the mid-frequency asymptote here between F1 and F2? So for F between F1 and F2, we can write A of S as follows. If we're at frequency higher than F1, so you can think of S as being j omega, and what is the magnitude of the j omega over omega 1 term relative to 1? Well, if omega is greater than omega 1, then this term has larger magnitude than the 1, and to write the equation of the asymptote, we throw out the 1. Okay. Likewise, for the denominator, what do we do? Well, over this frequency range, we're at a frequency less than F2, so we let S equal j omega, and omega is less than omega 2. That means that this second denominator term will be smaller in magnitude than 1, so we throw that term out. And what we get then is A of S is A0 times the numerator, S over omega 1. Then for the denominator, we just have 1. And that's our function. Now if we want to take the magnitude will be the magnitude of A0, which is the real number, times the magnitude of this numerator with S equals j omega. It gets us omega over omega 1, and then the denominator is 1. Okay, or in terms of F, we could also write this as A0 times F over F1. So that's the equation of the mid-frequency asymptote. Okay, it's very useful to be able to write the equations of asymptotes. When we design our feedback loops, we're going to need to do this to calculate things like the crossover frequency and other quantities that we need to know. Okay, I'm going to write our A of S again. Let's write the equation of the high frequency asymptote. For F greater than F2, which is in turn greater than F1, what can we say about this high frequency asymptote? Well, again, when we have a sum, we take the largest term and throw out the smallest. So here, S is larger, omega is larger than both omega 1 and omega 2, so the terms on the right are the largest, and we can throw out the 1 in both cases. So A of S then will have an asymptote, or we can say A of S is approximately equal to A naught times the S over omega 1 in the numerator, and the S over omega 2 in the denominator. Let's see, the S's cancel out, and we get A0 times omega 2 over omega 1, or in terms of F, A0 times F2 over F1. So that's the equation of this high frequency asymptote. Now here the high frequency asymptote is labeled A infinity. It's just the value of the asymptote. So A infinity apparently is given by that expression. So we have a straightforward way to easily write the equations of the asymptotes by simply taking the largest term wherever we have a sum of terms. And here this also gives us an easy way to find, say, the high frequency gain in terms of the low frequency gain. Okay, these slides 35 and 36 document what I just said. Now there's one other way to write the transfer function that can be very useful. Suppose we're not interested in A0, or it's not so important in our application. Suppose instead we're more interested in the high frequency gain. We could express A in terms of the high frequency gain instead of the low frequency gain. And what we do is we use inverted forms. So if we use inverted poles and zeros, each of those kind of terms has a high frequency gain of 1 or 0 dB. So if we express our transfer function in terms of inverted forms only, then we know that each of these forms will be 1 at high frequency, and then any multiplying constant out in front is in fact the high frequency gain of the transfer function. So if we take that viewpoint, we start with a high frequency gain of A infinity, and if we decrease frequency below F2, the gain decreases. So that is in fact what a pole does, and this is an inverted form, so 1 plus omega 2 over s would cause our transfer function to decrease. And then when we get to F1, the slope increases again as we decrease frequency, so this is an inverted 0. So we can put an inverted form 0 in our expression as well. This happens at F1. So this is another completely equivalent way to write the transfer function. This way of writing the transfer function emphasizes the high frequency gain rather than the low frequency gain. And if that is what is important in our application, then that's a good way to write the term. I'll leave it to you to verify by algebra that this form is in fact equivalent to the original form with non-inverted poles and zeros. One last application of inverted poles and zeros. Suppose we're interested in a transfer function that is a bandpass filter. So let's suppose we want, say, a transfer function like this, where this slope is plus 40 dB per decade. This is plus 20. This is a flat slope at this midband gain. This slope is minus 20, and this slope is minus 40. How should we write the transfer function of this? Well, what I would suggest is the easiest way is to reference our transfer function to the midband gain. In a bandpass filter, that's usually what we're interested in. So we will write A of S is equal to the midband gain A sub m multiplied by some poles and zeros. And these poles in zero terms have to be chosen such that each of them gives a gain of 1 or 0 dB over this midband range of frequencies. And then these terms can make the gain roll off at higher frequency or lower frequency. Well, so what we can do is first we can have regular poles at omega 3 and omega 4, like this. Okay, these poles give 0 dB gains at frequencies below omega 3 and omega 4, but over the important midband range of frequencies, their gains asymptotes are 1. Then for the omega 2 and omega 1 corner frequencies, we use inverted forms. The inverted forms will cause the transfer function to roll off at low frequency, but they will have 0 dB asymptotes over the midband and higher frequencies. So we can have an inverted pole at omega 2 and an inverted pole at omega 1. and the numerator apparently is just 1. So this is a valid way to write this transfer function. It mixes both regular and inverted forms, but it's written directly in terms of the things that are important. So it expresses the midband gain directly here, and then it gives each of the corner frequencies with an appropriate term. So this is another example of how to use inverted form terms to make the transfer function be meaningful and straightforward.